I graded the tests, but I forgot to bring them. So if you guys are particular after the class, let me go and get it. It shouldn't take too much. 2 minutes. You might want to see. Just tell them that change the camera to you. Where am I? Look, I'm not even connected. What? Oh yeah, where am I? Yeah, it's you guys. Yeah, I'm just looking for myself. I'm saying I'm not there. Yeah, okay, so yeah, so it's just connected now, right?
How did you do with this?
I think it was like a 90.
62. First problem, I knew I wasn't gonna do well on. So,
Yeah, messed up on that one too.
third problem, I definitely had a lot of trouble with.
On the recurrence one.
Yeah.
Yeah, on that one I just started with like L equals 1, I think, and then solved it for PL2, and then used L equals 2, and then just like kept doing that until I got to 4.
Yeah, I was getting confused like, when I was doing it because like, I got like PL of x equals, or P1 of x equals P2 of x, or something like that.
Mm-hmm.
I didn't know what to do with that.
Yeah, I think I just like, because it gave what P0 and P1 were, I think, so I used those two and found P2, and I used P2 and P1 and found P3. And it goes that way. Oh, and then the fourth one, I think that I remembered the right formula for the interval or whatever. I think we're gonna have to know that.
The fourth problem.
Uh-huh.
Yeah. I think I remember
Mhm.
because that one you have 2 answers.
Uh-huh.
Okay.
Yeah, just the two.
Yeah, the quadruple kind of threw me off since it was 4 points.
Mhm. Yeah, I think I got 0 along the diagonal on that one, and there's like a 3 for the IJ and the JI. Yeah.
So for your monopole, you have 0.
Uh-huh.
And dipole, 0. Yeah, I get that.
So I cannot obviously pass on the test to you guys, right? So if you ever come to the campus, collect with me, or if you really want me to scan and send it to you, then I can do that. But just send me an email. I don't want to scan everyone's. Is that reasonable, Matt and Curtis?
Yeah, it's reasonable. I'll probably just shoot you an email and come get it at some point.
Yeah, that's the easiest. But if you really want it, I can scan it. Just send an email to me. Okay. How was the exam? Was it reasonable? I heard one comment that it was harder than expected. Any other comments? No. Prefer to stay quiet. Okay. Yeah. Okay. Talk to me about your grades. I think that's the best thing. Yeah, I would say I'll recommend you guys to talk to me how to proceed if you have a exceptionally good grade, that's no problem. But if it is lower, I would say talk to me. Oh, I should say that I haven't curved the grade yet, right? Yeah, I haven't curved the grade. I just graded the exams and put it. Usually I give some points back. So especially for those who are the lower side, you gain a lot. So I'll try to do that in the next few days. And that should, and then I'll post the grades again. So I should be able to give you the statistics after that. Okay. Any other general comments? How course is going? How it should go? Anything at all? Okay. Not be going. So there is homework 9 I posted just a few minutes back. Made it due Monday, October 19th. And I think midterm 3 should be, actually don't know. Should be somewhere in November. So it's not very close, but I don't remember if it's
Number 6.
November 6th. Okay, thank you. And which day is it?
Friday.
Right. Okay. And I think Thanksgiving begins on 19th or something.
Yeah, after that we have like 2 weeks of
2 weeks in
in-person school.
Okay. Yeah. And then after Thanksgiving, we have only 1 week of school. So 3 weeks of classes. Actually. Yeah, that makes sense. Okay. So today, I want to talk about how we have talked about how we find the electric potential and electric field due to a charge distribution, but now we want to talk about material distributions. What if it's a material? What property of a material actually contributes to the field? So it's called electric polarization. And we'll stick to electrostatics. We want to magnetism. Later on, when we do magnetism, we can talk about the magnetic properties. So remember electrostatics, our equations are del charged with E is equal to, let me actually start writing it as epsilon naught front of the electric field. That's equal to charge density. Right? There is no time dependence. And we have cross E. The curl of the electric field is equal to 0. And what we would like to talk about is what if there was a material now? Like if there was a positive charge here, we know how to do that. But now what if there is an additional material? And by material, what do we mean is that this is neutral. Positive, negative, positive, so 3, 4, right? 1, 2, 3, 4, 5. So it's a neutral charge, and its distribution could be anything, but we did realize that we pointed out that there are multiple moments, so even if something is neutral, it might actually have a dipole moment. So this material will actually interact with this, especially if it has a dipole moment. So if it has a dipole moment and a charge, that could be interaction. But we would like to make this more concrete because this is lots of atoms there, right? It is 10 raised to 23 of them. So we need to have some average property there. It is the dipole moment, but we want to make this more concrete. So with that purpose, so let's think of an atom. So our goal will be to first see how we think of an atom, and from that point we will build a material. So let's say charges, right? So electrons and protons. So charges build an atom builds a material, right? Or lots of atoms, lots of charges make up an atom, and lots of atoms make up a material. So that's what we want to think of. So let's say, so the individual charges of an atom. So let's say this is an atom. So that's an atom. There is no such fixed spherical region for an atom, but there are charges around. So that's your positive usually is somewhere at the center, right? There are lots of positive charges, right? And then there could be negative charges around here like this, right? But randomly, it's no such pattern in there. But whatever it is, if we have a coordinate system, I can think of some point R, not necessarily the center of the atom, and each of these charges has a position Ri. And let's say that each of these charges is Qi, Q1, Q2, Q3. So this could be Q2 and with position R2, Q3, and so on. And an atom by definition is neutral. So it is clear that the sum of the charges, notice I might be summing over a large number of charges, like there could be 56 electrons in there and 56 protons. So, but whatever it is, you're saying that's 0. That's going to be the definition of the material and an atom that builds a material. Next is, of course, the dipole moment, and you can say its dipole moment will be summation over Qi times if its charge, if its total charge is 0, its dipole moment does not depend on which origin you choose. So I can choose any origin I want, and I will pick a point R somewhere inside the atom, and this is Ri minus of R. So even though your origin might be somewhere here next to you in a lab, but with respect to some point R, I can have a reference point. Then it doesn't matter because what is this equal to? What is that? This is I, Qi, Ri, and minus of I, Qi, times again the vector R, this doesn't contribute because this is a constant, right? That's equal to 0. This is equal to 0. So the position R actually doesn't matter. Wherever you want, you can pick this. So you can choose the position to the nucleus or any other point, and you're perfectly good with that. But we will pick something suitable so that it's inside sort of the center of the charge if you want, but it doesn't have anything specific to associate. And this will be called the dipole moment of the atom. If you want, you can write atom underneath, but that's the dipole moment of atom. Okay, so it's good. So let's ask, what is the force acting on this atom if I were to put this atom in an electric field? Like if I want to know, so remember, if there was a point charge, if there is a point charge with charge Q, then the force is equal to Q times the electric field. If you think of it as a density, I can also say this is a force per unit volume, which is often we say this is small f, is equal to, so this now depends on charge at position R and the electric field at position R. Here also at the same thing, this is the position of the charge Q. This is the electric field, not any point. If the electric field is different at different points, it is a position of the charge that decides where that is. Similarly, this is the force is charge density times the electric field. Now, how do I know what a material will do or an atom? So how does an atom work in a if you exert an electric field? Christian?
For the top equation, what is that subscript?
This is Q, position of the charge Q. So this is Q. Is that better?
Mm-hmm.
So a charge sits at a position and it is the electric field at that point times the charge that. Now, if you keep an atom in an electric field, we can ask what is its charge distribution. So that's going to be this. But we would like to, whatever comes up here, right, times your electric field. That's what we are interested in. So let's say this is R. That's the position of the atom. And whatever sits here, is it going to be the charge distribution? We're not sure about that. So this will be called rho effective. So whatever comes here, we'll call it rho effective. So that's the characteristic. So electric property of the material, of the atom actually. And using the atom, we will build the material. So this will go into the material. Okay, is that clear? So is the motivation clear? Like this is, if we have a point charge, that's Q. What does it sit here? You have an atom. And for an atom, it is reasonably easy. So let's start with the force on the atom, right? How do you calculate the force on the atom? Put it in an electric field. You put it in an external electric field, not necessarily constant. So this will be equal to sum over. So a single charge will experience Qi times the electric field. If there are lots of charges, you just add them all, right? Vectorially add them all. So I is equal to 1 to say 56 charges, or 56 if there are 56 electrons, then 56 into 2, right? Neutral. Protons are also there. And it's a position also that comes in, right? Position of the charges. At each point there is a force, so they all could be in different directions. but they can cancel also. Most of them cancel, right? For example, if there was a positive and a negative charge, if you put in an electric field, this might experience an force here, F1, and F2 might be here, and mostly they cancel out, right? Unless there is a electric field difference between the two positions, there will be a difference in the forces. Is that clear? Like roughly picturization of that. So, what is this equal to? We want to make an approximation now. So, since these are all very close points, right? So we can presume that the electric field here is reasonably close to the electric field there. So is that at all or not? So let's let's expand this electric field as a Taylor expansion about the point R. So in that sense, this point R now gets some significance, that even though we said that's arbitrary, it could be anywhere. But the point is that whether it is this point or that point, the change in electric field is reasonably small. So it is plus. Now Taylor expand this, and Taylor expansion in 3 dimensions, remember, is Ri minus capital R. And that's a change from this point, and dotted with a gradient with respect to R of the electric field evaluated at R. We did this a little bit when we were doing legendary polynomials, this way of Taylor expanding. It's the same idea. And there are higher orders. Okay. And when can we drop this higher order? So let's say that we are actually going to talk about the approximation that we're talking about is Ri minus R. So that's a distance, right? So the distance, you can think of it as distance between different charges. And this should be very much small compared to some characteristic property of the material itself. And that's going to be, what do we mean by characteristic property? Something that repeats. For example, if you have a crystal, atoms repeat after a certain point, right? So that associates a length to it. So that will be a characteristic length. Right? So that should be significantly small. And so let's say that's wavelength. This should be significantly smaller than that wavelength. Often it is not even that crystal length that comes in, there is significantly larger quantity that's involved in that. And this is a very good approximation. Often you don't need to do anything more than that. It's a very good approximation in there. So this is the approximation in which we are working. And that means that if this contributes, then this is going to be very small. If this contributes, then this is very small. But what is the first piece? So in that case, so let's do this. This is equal to I times QI. What is electric field at point R does not depend on the sum. So I can forget that these times. Right. So basically the same sum, but I put some parentheses to clarify that this sum can be done at this stage first because this does not depend on that sum, right? I factor that out. Plus, same thing again, the sum doesn't depend on certain quantities, so that's Qi times Ri minus R. So again, put some parentheses, started with so again, I put the parentheses just to signify that the sum doesn't go beyond that. And I can factor these things out of each of the term. And then you see that, oh, that's nothing but a charge, total charge of the atom, that's 0. That's 0. So the next is dipole moment, and it turns out that this is actually the total dipole moment of the atom. This was the total dipole moment of the atom, and that's all there is. Which makes sense. We already intuitively thought that if there is an atom, it is going to be the dipole moment that's going to interact with the electric field, and it does, but it is a gradient that it interacts with. Right? So that's equal to that's 0. So it is dipole moment dotted with gradient with respect to r, but I don't really have to write it. There is nothing else, right? It has to be r. What else? Right. And remember, we would like this to be our, if we can identify force is something times the electric field, that's our effective charge, but that's not really convenient because the gradient actually acts on the electric field. Right? It's not there still. And remember, this is still an atom, right? This is a force on an atom. So maybe I should signify that as a force on an atom. We are interested in the force on the material, right? That's what we would like to do. So let's proceed and do some more on it. So force on an atom, again, just rewriting it, is equal to the dipole moment of an atom. So let me write that dipole moment of an atom dotted with gradient. The electric field at the now R is the position of the atom now, right? In that sense of looking at it, so there is some central point of the atom where the electric field doesn't change too much, and that's the position of it. And our approximation says that you can pick any point you want, you could. We're saying that the electric field doesn't change too much in the region of the atom. Okay, so now we want to make a material out of this. So force on a material is going to be, here is sum over all the force on the atoms, sum over all the atoms. But now that's a very, usually when it comes to charges, there are only about 100 of them. But when you're talking about integrating over atoms on a typical material, you're really talking about 10 raised to 23 of them. And in that case, this is reasonable to say that this is an integral. So again, it's approximation, but that's very reasonable. So this is d cube r, right? And in a material, not everything is filled with atoms. So this is a force on an atom. So I have to give some property which characterizes in a certain volume there are how many of them. So you say this is number density. So this is n of r. Okay, so this is at some volume there are a lot of atoms. So this is number density, and n of r is equal to number of atoms per unit volume. So what we are saying is that d cube r is a small tiny element of volume, and we ask how many atoms are there in that tiny element. This is an infinitely small volume, but somewhere we are making this continuous, and we are saying that this is a continuous distribution at each point. The number density decides how many atoms, and that's our characteristic property. So two things: dipole moment of an atom and the number density of the atoms is what we have introduced as of now to characterize our material. So now let's see what we can do from here. This is d cube r times number density, but we know this is nothing but atom, right? So this is the atoms, each atom, dipole moment of each atom, dotted with gradient of electric field. And at this point, since we are making this continuous, now I can go back to my small variable r, right? So because I'm integrating over the r.
At every point there is an electric field. This is now at each point inside of the material there is a number density, and at each point there is a dipole moment of the atom. This is what is called electric polarization. Electric polarization of the material is a vector which is there at each point in the atom, and you ask how much strength of dipole moment is there at each point. R times P atom. To give a feel for this, remember that you can think of each atom as a dipole. So this is a dipole, this is a dipole, this is a dipole. It's a material here. So this is your D, and how many of them are there? So that break up into dipole moment. Microscopic dipoles will give you a macroscopic dipole moment. So this is microscopic. Each atom has a, and you just sweep it with respect to the number density, and you get something a macroscopic. Any questions at this stage? So this is what is called the electric polarization. Electric polarization. Like if you've done undergraduate physics, there we define what is called a dielectric constant. Those are all related to this. So this is the material property that decides how much a capacitor will charge, and so on. That's a material property. Any material, that's your electric. So when we say epsilon naught, is that epsilon naught is your dielectric, dielectric permittivity of vacuum. That's related to this, and very soon we will talk about what is epsilon of a material also. But at this stage, this is the electric polarization. Okay, so that's good, but we still are interested. Our goal is to find out what is this, right? How does a material interact with an electric field? So we go back here and put this in there, right? So force on a material is equal to integral. Right? Now this is a property of this material, so it's a R and then dotted the gradient if you want, or electric field. Again, if we were to compare with this seems like this is your charge density, but that's an operator acting on that, so that's not very useful. But this is an integral, so we make the trick that I can actually integrate by parts and put it on the left hand side, but then there will be a boundary term. So let's investigate that. So let me write this as a, so this is differentiation by parts trick. So instead of writing this gradient acting only on the electric field, let me make it act on both. Right? So this is not correct, obviously. Times the electric field. And here the gradient is acting only on the electric field. Here it is acting on the electric field and the polarization. That's a mistake. Right? And the dot is with the first vector P. So that's a mistake. So you have to subtract that mistake. So you subtract the mistake, and that is you have to subtract when it acts on P alone. So that's del charted with P. And let me, so there is an R dependence here, but you not write it. Instead of P. Let me write it. Okay. This is a total derivative, and total derivative contributes only at the boundary. Like whenever we integrate by parts, there is a boundary term and there is a differentiation on the other piece. So this is the boundary of where are we integrating? We are integrating over all space. We can integrate over all space. And when I do that, at the boundary, we don't have a material at the boundary. Right? We don't expect that to be a material completely filling the universe. So there is no boundary at the edge of the universe, so that's 0. Right? This is equal to 0 at the boundary. So this term doesn't contribute. So this term, this whole thing goes away. This is equal to 0. That's equal to, so then that's only the second piece that contributes. That's dq bar minus p, or let me write it like this, dotted with electric field. And now if you compare it with your first earlier strategy that, oh, if I can actually, oh, let's put down. If I were to compare this with my earlier strategy we built was that let's have an effective charge, right? So if I compare these two, it seems like this is your effective charge of the material. So a material has a charge actually, and even though it is neutral, effectively it has a charge, and that's given by gradient of the density of the dipoles. So yeah, that's a good thing to say. Like, this is electric polarization, but that's just density of the dipoles. This is dipoles per unit of volume. So this is the gradient of the density of the dipoles. So the effective charge is divergence actually. Divergence of the density of dipoles, the microscopic dipoles. So if we go back now, so if there is a material, we go back to our first Maxwell's equation. So this is your macroscopic equations, macroscopic electrostatics, let's say. It's not a complete Maxwell's equation because we're not doing magnetic field still, and we are statics, we're working in statics. So now we say, you know, dotted with epsilon naught times electric field. There are two ways you can get a charge density. One could be the charges itself. This could be the proper charge. That's there. But there could also be a material contribution, and you say that's rho effective. And your del cross is of course 0. And this is nothing but rho minus del P. Of course, del cross E is always 0. Often you put this on the left hand side. You say this is dotted with epsilon naught E plus P is equal to rho. So now notice what is happening. Here, there are two ways of looking at it. If there is a material, it creates an effective charge density. And so there is a divergence of the density of the dipoles contributes to the electric field, but the polarization itself appears as a divergence, so you can bring it up here. So this interpretation tells you that the material actually changes the electric field, right? Which is what we see, right? If, for example, if you had to actually exert an electric field here, inside the material, there might be some alignment here, positive charges here, negative charges there, and there will be an electric field. Oh, the positive will go that side, right? Positive there and negative there. And there will be an electric field that's generated by this induced charges, and that will change the electric field. And that's this. That's your polarization. So the effective electric field is different inside the material. The dipoles are contributing to it, and there is a change in there. And this is often called D, right? This is called a displacement vector. So D is equal to epsilon naught E plus P. So our Maxwell's equations become del with D is equal to rho, same as your old equation, but now there is a D is equal to 0, and our understanding is that D actually is equal to epsilon naught times E plus P. This is the polarization in the material itself, and our what we're imagining is that this material has some fixed polarization, like charges are aligned in a sense, or there is possibility for an alignment. But there is a one more point one can add to this. So what you want to take home from this whole thing is that if you have a material, it has a property called P, the electric polarization, and it contributes to an effective charge density, which can be thought of as the electric field itself. That's the main content of this whole discussion. But there are possible, so there are two types of materials. So one is, so first is materials with permanent polarization. Materials with permanent polarization. And in that case, not much happens. It's just D is equal to epsilon E plus P. That's it. If D is the permanent polarization, you cannot do. And the second is materials that are a little flexible in the sense that these dipoles can move around, like especially they can rotate around. Materials with induced polarization. And that means to say that if you have a material, if I have a dipole D, like there's a negative and a positive, so that's your dipole. If I exert an electric field, this can align with it, right? So its polarization actually is affected by this electric field. And what you say is that this P is proportional to the electric field. It can depend on the electric field. Now it can depend in many ways, right? It could depend on the square of the electric field. It could depend on the cube of the electric field. It could be a complete function of that electric field. But if it's a linear material, we say this is alpha, like or chi. And in general, yeah, let me just say this is chi. And let's put it as epsilon naught. So this is, notice, this was a permanent polarization. Here the polarization is getting affected by the electric field, and assumption is that this is a linear material. Like a material that depends on the electric field linearly. If it is square, they are less, it's not very common to have that, but of course one can have such materials. Often we work with simple materials. Okay, so if that is the case, so this is induced now. This is induced polarization. Then what is your displacement vector? That's epsilon naught times electric field plus I naught times I times electric field. And that whole thing can be collected together. Epsilon naught times chi times chi plus 1. And since it's our old electric field that affects, and that's our more interesting part, you define this to be, so let's say define this as epsilon times an electric field. And there is a definition there. So definition is that chi naught and you see that chi is equal to over epsilon naught minus 1. Right? Lots of definitions in here. T is induced polarization. Like one of this is decided by the other. Once you, if it is linearly dependent on the electric field, you have chi, which is your electric susceptibility. And epsilon is your electric permittivity. Of the material, of the material. And I think kappa is equal to epsilon over epsilon naught. This is the dielectric constant. If one of this is given, each other is related. In this week, whenever we work with the material, we won't talk about induced polarization so much. We will work with permanent polarization. So that's what all the homework problems will be based on, permanent polarization. So the point is, if we are given permanent polarization, the divergence of that gives you the effective charge density. And the moment you have effective charge density, then you can do your old physics. Right? Then you pretend that that's your charge density and go from. And we will do specific examples on Wednesday and Friday, and we can go from. So the main point is that what is the definition of electric polarization? Now we have materials. That's all. And one of the extreme, I should say, is that there is a conductor, right? In the limit when P tends to infinity, that's what a conductor is. It's a perfect conductor. Its P is large. The dipole moment is very large. That's all. Thank you.